So here we are then in the last video of the series. We're going to look at trying to fine tune an embedding model. And basically the whole point of this series of videos is because we don't actually need a huge amount of technical expertise to set up these RAG systems. I mean, we need some sort of familiarity with how these libraries work, etc. But we don't need to be data science experts to get the systems to function well. Now, what I'm going to show you is some, I don't know what I'd call it, some off-the-shelf fine-tuning. And now if you're fine-tuning an embedding model, essentially you could be writing, you'd want to write the code yourself in PyTorch, and you'd want to watch the training, see how it's going, modify the training, and get as much out of the fine-tuning as you possibly could. Now, there's wrapper functions which are very easy to use. We're not going to have access to all the technical side of it, but we're essentially, and I'm going to show you today, how we can just take some data and take some embedding model, throw this through a fine-tuning function. That's all going to go on, and we're not necessarily going to see too much of what's going on under the hood, but you will see that we are still going to get back something which is more powerful than we put in. So you don't necessarily need to be an expert if you're dealing with one of these sort of wrapper functions where everything's being dealt with in the background. And I say to you again, yeah, of course, maybe this is not going to get you the best results, but you're going to see in this video it's going to get you some very powerful results with very little work. So let's zoom in. Again, I'm going to go through this notebook. It's already been pre-calculated, and we're going to be looking at some of the printouts from Colab. So here we go. Again, I'm going to be dealing with this Theft Act from 1968, the UK Theft Act. I'm getting my LangChain libraries, my PDF readers, my text splitters. I'm getting that document, I'm splitting it up, as we saw in the last video with this character text splitter. So I'm essentially getting paragraphs of a legal document. Now, here I've used LangChain because I wanted this function, which is very easy to split up my documents, but to do the fine-tuning here is actually a llama index method. So all I'm going to do is use this function I've written to go through each of my LangChain document, take out the text content or the page content from each of those LangChain documents and post that directly into a llama index text node. And like that, I've converted my dataset from LangChain into llama index. And I have a list of llama index text nodes. So that's ideal. Now, once we've done that, we are going to go out to Hugging Face and we are going to find the embedding model that we wish to test. And we are going to be using this BGE small. Just zoom in a little bit more. Okay, so I'm in llama index. I've got my instance of settings. I hang my embedding model on that settings. And then I'm going to go out to llama index fine tuning, and I'm going to ask for this generate QA embedding pairs. And we've seen this before. If we want to compare and contrast different embedding models, we're going to need to have some ground truth data. So we need questions. So we can then ask, okay, here's a question. Find me the text chunk. And we can see if our models have been able to do that. So essentially, we need the real answer to our question. So we're going to need to generate questions. And there you go. This code here, which I've securely commented out, so I don't start making calls, too many calls to GPT-4. We pass it the list of nodes, we pass it the large language model, it generates us questions, and then we've got this data set. And like we've seen before, this has got the queries, which are the questions, differentiate between robbery and burglary as described in the context information. We've got our questions. We've got our corpus, which is the original text that we split up, and then we have this relevant document, and the relevant document allows us to make an association between the corpus. So for any question, I can find with the relevant document the ID of the text chunk. So that's all we need. Now we move on to the actual fine-tuning, and if you have a look at this notebook in slow time, it talks essentially about the loss function, which is used in order to fine-tune this model. So if you know about neural networks, you know that we need to define some sort of loss function, which is then going to tell the network how right or how wrong it was, and then we're going to adjust the parameters of the model to slightly improve on those results, and it's an iterative process. Now that information is available. This is the loss function, which is going to be used by the fine-tuning that we're doing, and essentially all that's going on here is that we have some anchor. It's called an anchor. That's the target embedding for some text, and we're going to have some other similar text, and we're going to have some different text. And so each time we do this, we have this anchor, something which is similar and something which is different, and the aim of the game is to adjust the model parameters so that our embedding gets closer to the thing which is similar and gets further away from the text which is different. So that's how it works under the hood, but let's not get too bogged down in that. Again, the whole purpose of this video is to show you how we can get these results without the pain of being some sort of technical expert. So this fine-tuning then. Here it is, Sentence Transformers Fine-Tune Engine. We're going to give it some stuff, the trained data set. We're going to give it the model that from Hugging Face that we want to fine-tune. We are going to save our fine-tune model somewhere, and we are going to say how many epochs. That's how many times we're going to go through the entirety of our data during this training process. And in addition, we can add a validation data set. We can get a little bit more information to tell us how the training is doing, but we're not going to do that. We're just going to say fine-tune this for a bit of time. We're going to take whatever comes out the other side, and we're going to see what happens. So once we've set up this fine-tuning instance, all we need to do is call OK, fine-tune it, and we get some sort of return back as the fine-tuning is going on. You're going to want to be using the GPU to do this, otherwise it's going to take far too long. And then we can get our fine-tuned model. We can even save that locally. We can get all the details down into JSON. We can zip it up, and we can store that locally if we want to, or we're just going to refer to it in the rest of this notebook. Now the evaluation, we've seen it before. We're just going to be looking at the mean reciprocal rank. So essentially we are going to give a question to the embedding model, and it's going to give us a list of the best documents, the best chunks. We know that question was generated from chunk X. We're going to look at the position of chunk X in the recommendations from the embedding model, and say if it's number 3, then we're going to give that a score of 1/3. And we're going to take an average of all of these scores. And so in order to do that, then we've got this evaluate function, and you can look at this in slow time. And there are going to be off-the-shelf evaluation functions that you can use. I'm doing this one myself, and we just calculate that mean reciprocal rank for our embedding model. And I'll let you look at that in slow time, and we get some sort of score. Now, remember here, we had a score for our small embedding model. That's the model that hasn't been modified. And then we've got this fine-tuned model. If we evaluate that fine-tuned model, we see that the mean reciprocal rank has gone up significantly by about 9 points, which is a big jump. So here we haven't had we haven't looked at the fine-tuning process. We've basically just used this function. We've just thrown our model in and say train on that data set, and we've taken whatever's come out the other side, and you see here with very little effort at all we've come up with a model which is better. Now, of course, if we took care and attention with this fine-tuning process, we're going to get even better results. But you can see here we've got an improvement for very little work, but there is a problem with these results. And the problem is that we fine-tuned our data set using the Theft Act 1968. And so our model learnt how to embed these vectors for the Theft Act 1968, but now we test it on the Theft Act 1968. So we're basically testing our model on the data that was used to train the model, and this is of course unfair, and it potentially won't generalize to other data. I mean, if we keep going, we can get amazing scores on the Theft Act 1968, but we'll basically have just trained a model that has learnt the Theft Act 1968 and is completely useless for any other task. And that is called overfitting. And we want to know if these results generalize, so we are going to need, and we'll just check the time, we'll just have time to look at this. Yeah, we're going to need another data set which is a similar problem. So before we do that, we're going to look at the model from OpenAI, and we can see that it gets a score of 81. So that's lower, it's higher than our small embedding model, but it's lower than our fine-tuned model. It's significantly lower than our fine-tuned model. We get a test set here. This is going to be the Fraud Act from 2006. So this is something that our fine-tuning hasn't seen. We're going to generate documents with that, and then we're going to go through the same process of evaluating each of our embedding models on that unseen data. And we see that the small model on this data set, it must be slightly easier, gets 82. A fine-tuned model is at 85, and our OpenAI model is at 83.5. So we see essentially then that fine-tuning has worked. It has generalized. It's not as big a jump as we saw from the other data set, but it does generalize. We've created a fine-tuning model which is more powerful than a small model, and crucially now, using that small open source model, fine-tuning on it, we've actually got a model for this particular task with very little pain, which is better than anything that OpenAI can offer. So you can see the power of fine-tuning. And so that's all for this mini series. I hope it's been a good introduction to RAG. I've taken you from the first notebook, which is a very quick setup of a RAG system, and we've moved through some different concepts and started looking at how we can optimize parts of this RAG pipeline. So I hope that has been useful, and I'll see you guys next time.